I'll keep letting people in as we go, but I want to introduce our special guest speaker today, the creator of OpenResty, Yichun Zhang. So I'm very excited for this class. I hope you all are as well. And I'm going to kick it right over to him to begin his talk.
Hi, everyone. Okay, shall we begin now?
Yep, go ahead and begin. Thanks.
Okay, great. I'll share my screen. Okay, so glad to meet you here, everyone. And I'm Yichun Zhang, the creator of OpenResty and also the founder of OpenResty Inc. And today I'm very happy to share the topic of domain-specific languages from the OpenResty perspective. And we will focus on the implementation strategies and technologies in this session. We may briefly cover some design considerations of DSLs as well. Okay, so feel free to interrupt me with any questions during the session. We will also have a dedicated questions and answer session in the end. Hopefully we can have helpful communications today. Okay, so I'll give a longer introduction of myself. So my name is Yichun Zhang, and I'm creator of the open source OpenResty project. So basically we build a web application platform and a web server platform based on LuaJIT and NX with our own abstraction layers like lightweight threads and coroutine based on coroutines and other advanced features. And OpenResty is currently the third largest web servers over the internet, right behind like NX and Apache HTTP. And I'm CEO and founder of OpenResty Inc. company, a US company, and I'm also a former founding team member of Cloudflare, which is a CDN security company. And I'm also a former technical expert at Taobao Alibaba, the largest e-commerce website in China. And also I worked as a former senior engineer at Yahoo. Okay, so why Lua and LuaJIT? So I think you guys are here because you guys love Lua already. At least you are interested in Lua. But still, I'd like to highlight some of the advantages or benefits of the Lua language and also the LuaJIT implementation. So LuaJIT is a very efficient interpreter and also a very fast tracing-based JIT compiler. I won't expand on the tracing part because that should be another presentation. And LuaJIT also has a very small memory footprint. So for real business grade applications, we observe like 50% smaller memory usage as compared with the standard Lua 5.1 interpreter. But that result was many years ago. And it's also very extremely lightweight coroutines are built into LuaJIT and also the standard Lua interpreter, of course. And they can be used to do transparent I/O multiplexing and non-blocking I/O. So for some of the DSLs, we really need to take advantage of such I/O capability because that allows like C10K or C1 or even 1000K, C1000K concurrency support. Okay, and also it has a very great C interoperability via FFI, so that's the LuaJITs you mentioned, and it's very efficient and can be just in time compiled. It's also it also supports the standard Lua's C API, which is a VM level. And it also supports explicit bytecode representation, which helps separating the compiling and execution phases, which helps a lot actually for a lot of Lua code input, because even though the Lua parser is fast, it still takes time for a huge amount of code base. Okay, and it's also easy to hack. So the code base is small, especially for standard Lua interpreter, of course. It's very small. LuaJIT is bigger, of course, because of all the optimizations. And also it contains two implementations. One is the JIT compiler, and another one is the interpreter written in handcrafted assembly. Okay, and but still it's small. The LuaJIT is so small that compiling everything only takes a couple of seconds on a modern computer. Okay, and it also has great portability with a lot of different architectures and operating systems. It also has an efficient incremental mark and sweep garbage collector. And I know that recent versions of Lua, standard Lua interpreter, I mean, support generational GC, but for LuaJIT, it's still mark and sweep, non-generational GC at this point. But MicroPort designs a new GC, which is very promising, but nobody has implemented it yet, to my knowledge. Okay, and it's also great for a common language runtime for different dynamic languages or DSLs. So for this part, we still need some extensions to the Lua language as well as to the VM to properly support some exotic languages, because Lua is a very minimal language by itself. So it still needs some extensions here. Okay, yeah, it can be a long list. I just mentioned like 10 or 12 here. Okay, so why DSLs? I know that this lesson or this course by the author of the Lua language is about implementing languages, especially the domain-specific languages. Okay, so I still want to mention some of the reasons behind DSLs. So the first reason is to communicate human intentions and knowledge more efficiently with machines. So because programming is all about communication, especially human-machine communications or interactions. It's essentially about telling machines what to do to achieve certain goals of the humans. So that's why we humans invent so many general purpose programming languages like Java, like Lua, like Python, Ruby, Prolog, Haskell, blah, 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 so many. And we also have some domain-specific languages that are very popular in the world already. I'll mention a few in a minute. And the second one is that domain experts, like mathematicians and physicists, they tend to use their own languages for their domains. So just like every mathematician tends to invent his or her own syntax or her own notations for every book, for every math books. So it's very natural to find the right syntax, the right way, the right language to express the current problems clearly, concisely, and beautifully. Yeah, the beauty part is human nature. And machines can also have more freedom in implementations and optimizations. This one is important, which divides the families of domain-specific languages and general-purpose programming languages. Because general-purpose programming languages focus on general capabilities and flexibilities. So they tend to be Turing complete. They tend to be able to do everything that is computable. But domain-specific languages are different. They, instead of telling machines exactly what to do and the sequence of those actions, it expresses the knowledge, high-level knowledge and intentions. So this way, we can free up the machines to find the best way to actually implement those intentions or knowledge or goals. Because many times machine can do a much better job to generate efficient code and do very aggressive and high-level optimizations than humans, at least the average programmers. So if we have a clean separation between knowledge and implementation, then we can always do optimizations, especially aggressive optimizations overnight, without touching the representations themselves. Okay, and this is a big topic, and we call it machine coding, one of the machine coding technologies. I won't expand too much here because that's also another big topic. Okay, and but still, DSL is a very important part of that vision, the machine coding vision. Okay, and there's another benefit for DSL, which can give much better error reporting and error handling on the business level than a general programming language. When using a general purpose programming language, one has to do all the error handling and error reporting themselves. Even with a library, it can be tedious and error prone and also a lot of work. And with a DSL, because it has a high level knowledge about the business model, about the business constraints, and all those things, so they can automatically do a lot of error handling and error reporting thanks to the compiler of the DSL. Okay, and also constraint enforcement. Any questions so far? No? Okay, let's continue. So we have some real world examples of DSLs. Many people are not even aware of them, but I bet everyone here has to know at least one of them. So first one is regular expressions. Okay, so the Lua language even provides its own, regular expression, but we won't call it regular expression because it has its own syntax. But still, it's a regular expression from the academic perspective. And one of the industrial standard for regular expression is the Perl compatible regular expressions, the Perl style, which is widely adopted by many languages and many communities, like .NET, like Java, like PHP, Python, Ruby, etc. Okay, and so regular expressions are so powerful when doing validation, data validations, and text processing, and even for essential for creating or implementing DSL compilers themselves, which we will see later in this presentation. And the second one is the BNF. So BNF is it's a very powerful DSL for expressing grammar rules for languages, and there are many extensions to the good old BNF language, which makes it even more powerful. And the BNF is also widely used in internet standard specification documents for describing some notation, syntaxes, things like that. Yeah, so it's a meta language for describing grammars or syntax of other languages, including itself. And also the mathematical languages using the Maple and Mathematica, those software. That's an example of mathematical style language, and SQL is so popular in the database world, especially the relational database. It's even embraced by those newer key value style databases. So it's a de facto standard for database queries and even database DDL, data definition languages. And the next one is the XPath. So XPath is very helpful for describing the to walk around, navigate through the XML documents, which is a tree-like documents. So that's also a very elegant way to express the intention to locate a certain node or certain nodes across the XML trees or web page document trees, because nowadays HTML documents are also XML documents per se. And CSS selectors are also very popular, and CSS is also a language by itself to styling a web page or something like that, so that we can add like fonts, like margins, and also colors, background colors, and even animations to the web contents. Okay, so we can see that DSLs are already everywhere, essentially. But still, for certain domains, we may want to invent our own DSLs to help with some kind of business models, some kind of software, and on some kind of industries. Questions so far? No. Okay, so the next one is something that very few people are aware of. So we talked about full-fledged DSLs, which we also call external DSLs, but there are also internal DSLs, which is for to borrow the body of a generic programming language for your own purposes, your own domain-specific purposes. So internal DSLs are a lazy way for implementing DSLs, because you can borrow the syntax, the parser of a full-fledged programming language like Ruby, like Perl, like Python, like Lua, like Haskell. So for example, the parsing libraries like parse for Haskell and LPEG for Lua. I know LPEG is started in this course by the Lua authors, and so they are, in my opinion, so they're essentially a way to describe something defined by the library itself. So instead of describing the generic computation, it describes it tries to mimic like a BNF, the BNF language we just talked about. In a Lua language or in a Haskell language, but by not introducing a new language. So for Perl, there's another example in Perl, which is the object-oriented programming in Perl. I mean, the native syntax is very poor. It's very limited, and so the Perl folks decide to invent a new library, which is called Moose, an animal name. So the Moose library tries to, use a function called like has, right, to emulate a keyword, but it's actually it actually is not. Okay, so the has keyword, but which is actually a function to define new attributes of a Perl class, and also they use the keyword like function names like is and is_a to define the type and also the visibility or other attributes of the attributes. Okay, so here is defines if it's a read and writable for the X attribute of this point class, and it's also this attribute has a type which is int integer, and the Y, so XY is coordinate attributes, obviously. And here we also define another class point3D, which defines a new attribute which is the. And then also it extends the parent class point. Okay, so extends also looks like a keyword, but it's actually a function call. It doesn't do much, but it's like a declaration. Okay, so yeah, so this is an example for using internal DSLs to serve your own purposes. It's very handy. Many people use that actually. But it still has some limitations. That's why we still need a full-fledged external DSL implementation. So regarding the limitations and the restrictions here, why the error reporting is a challenge. Okay, but it's still doable for many languages, still doable, but it's a challenge because you have to find the line number, for example, when something is wrong. Like the user use certain things in the wrong context or in just some wrong way, then you need to give an error message. The error message needs to find the correct line numbers and also give the correct messages. It's a challenge because everything is emulated by the host programming languages functions. So it's a quite challenge, but it's still doable with some level of work. And the second one, the syntax must be compatible with the host language. It's limited. Using function names and operators, like the arrow operator, which is essentially a common operator in Perl. So it could emulate some nice syntax, but it's still limited by the host language. For example, Lua is much more limiting than Perl, of course. So you almost always have to add a pair of parentheses there, and also you don't have a nice like arrow symbol here, so it's more restrictive. Okay, and the third one is is also restricted by the host language compiler runtime. You have to use the runtime, but there's way to work around that, like just generating a code in another language, right? It's doable, but usually internal DSLs are interpreters. They are more like interpreters instead of compilers. Okay, and it's limited by the host language's user base. So basically, the users of internal DSLs are usually just the users of the host programming language, at least a subset of it. It's very hard to convince users from other language communities to use your internal DSL hosted by a different language. Okay, and any questions here? No? Okay. Next one, we talk about the challenges in implementing external DSLs. So we won't focus on the internal DSLs here. We just mentioned it. This presentation is focusing on external ones. So basically, we need a parser, obviously, and a parsers include the tokenizer or lexers. We generally don't distinguish these two too much because for us we intend to use a top-down approach using a top-down algorithm like a recursive descendant algorithm for parsing. I know this course is about LPEC, so I bet that it's also a top-down recursive descendant strategy. There exist other strategies like the bottom up. It's not called like that. It's like like LALR algorithms. So those algorithms are much more efficient, but they also have some, peculiarities that we need to be careful about. Everyone working with the like a Bison or Bison or Yak, YACC, those full chains should know that there are some like shift complex, shift reduce complex, reduce complex, things like that. Yeah, so for top down, it's more natural, and in my opinion, it's also more powerful, because you can do some kind of context sensitive parsing. Usually, it's context insensitive parsing, but with top down algorithms, we can extend that to do some context sensitive parsing. So basically, especially when the lexer is integral part of the parser. So basically, if you try to parse certain grammar rule according to the grammar rule context, you can use a different tokenizer to parse certain symbols. So that can be very powerful. Such things are very tricky, if not totally impossible, in the LR or LALR algorithms, the bottom-up approach. Because in bottom-up approach, the context is not so natural, at least, but it's still possible. I think maybe it's still possible, but it's much trickier to get right. Okay, so the process we also can have some optimizations here, even for a top-down approach. So, for example, if you have many sub-rules, alternatives to try, you can do a parallel matching using a single state machine, so that you can immediately know which alternatives or prediction rules are matched for the current matching position. Yeah, well, I won't extend here. If we have more time, yeah, I can expand a little bit here. So it's a lot of fun. Okay, and there's another tricky part regarding the parser, which is about error recovery. So basically, modern compilers tend to generate as many error messages in many places as possible. So instead of stopping at the first error, it tries to pretend everything is still fine and continue parsing the rest of the text and just to find as many errors as possible. Yeah, for that part, it's really tricky to get exactly right. So, for example, you need some step holders, placeholders to insert when you really don't have enough information because you already had an error previously, right? So I think that's for advanced compilers and advanced users. For us, we don't bother. We just stop at the first error because that's the easiest thing to do. Okay, and also subsequent errors might be consequences of the first error. So it's very hard to really get as many unique errors as possible. Okay, and the second part commonly found in virtually all compilers, it's an intermediate representation. It could be anything, so it doesn't have to be in a particular form. But the most popular form is an abstract syntax tree or a parse tree. They are slightly different depending on how you define them. So the EST is generally represented by a tree. So that's a data representation, data structure representation for the input source code, for the input language. And there exists other forms of IRs. For example, in Lua, there's also it also has a IR that is in the form of SSA. Okay, so that's commonly found in traditional machine code generator generating compilers. So we won't talk too much about SSA because we here for DSLs we generally generate higher level language code. So it's essentially like a source to source translator. So we don't bother generating machine instructions directly, even though sometimes we may. Okay, and so I think some compilers may also use some kind of like bytecode. Yeah, it's a little bit similar to SSA instructions. Yeah, bytecode too for intermediate representation. But usually bytecode is not for analysis, in-depth analysis. It's usually just for serialization or just pre-compiling, things like that. Okay, so choosing the right form of IR for your DSL compiler is an art, actually. So it also depends on the actual use cases of your compiler. There's no silver bullet, and but in our experience, I think EST is the most convenient form. It's also the most common form for DSL or source-to-source translator compiler. Okay, and the third one is so it's more interesting. It's a context-sensitive analysis. Usually people call this thing like this, and or some people call it like semantic analysis. And also some optimizers are also doing things like this. So basically, it takes the IR form, like AST, and then walk around it, walk around the AST to gather information, do validations like type checking, like the other semantic analysis, and also optimizers to remove dead code and also find the conflicting or obvious errors, obvious semantic errors, and also do some preparation for the final code generation phase. Okay, so for this part, the code can be very convoluted because parsers can generally generate by some library, by some tools, because people don't usually write parsers by hand. But I think the standard Lua interpreter write the parsers by hand, but that's for ultimate performance or for ultimate control. Usually people don't do that. For context-sensitive analysis, it's very hard to find some automation tool, but there still exist some tools with limited success, I'd say. So I tried some of them, like the attribute language. I'm not sure if it's called like that. It's attribute language. So basically, it tries to define rules, doing matching and transformations across ASTs, trees like tree data structures like ASTs using a DSL. But it's not very it does not save much in my experience, but still you folks can try exploring here. So basically we try to use a more advanced language like Perl 6, so that writing such analysis can be very handy and be very easy instead of using Lua here. Okay, but if you really like Lua, so maybe you can still use Lua here. Okay, and the final phase is the code generation. The code generation part can be tricky if you are generating machine instructions directly. That's a whole worth of research and courses, but for generating code, that's usually much easier. Just generating code in higher level languages, like generating Python, Lua, C. So in our experience, or SQL even. So it depends on what you're trying to do. Okay, and in our experience, different languages are different when trying to generate the code in them. So certain languages are easier, certain languages are harder. So Python, I think, is a relatively hard one, but not too hard because of the indentation syntax. You have to be very careful to arrange the indentation levels in Python because they are meaningful and they are also critical if you mess it up. It's not just for aesthetic reasons in other languages like in Lua or in C. So you need to be very careful to keep track of the current and the next indentation level when generating Python code. And also Python is also a limited language as compared to Lua, because you cannot easily, for example, compose code blocks or code segments easily. Because Python, even though Python has some kind of the coroutine, not coroutine, it's closure function support, but it's still very limited. Because in Lua you can write whatever form, but in Python it's limited by some arrow form, some other strange limitations. Yeah, so that's something we need to be careful about. But even Lua has some drawbacks. We try to overcome those drawbacks as we will show in a minute. Okay, so for example, in Lua it doesn't have support for passing value by reference. You have to emulate that with some tricks, like through up values or through some tables. So such things are much easier in languages like Perl. So Perl is so handy. You can take an address or a reference of a variable, any variable, easily. And also the Perl syntax is also closer to C, and C for this reason is also a very perfect target language for compilers. But it also depends on what you are trying to do. It may not make sense at all. Okay, and yeah, so for code generation, so my point is that different languages may have their own pitfalls. Yeah, and also you may hit some really deep pitfalls of Lua, for example. You need to add a semicolon, right? So usually we don't do that, but when you are generating Lua code, you may hit those corner cases where you have to add a semicolon more often than in the real world. Okay, and also there are other limitations like the number of total local variables in Lua JIT. So you need to be careful to organize the generated code to avoid hitting those limitations, like the maximum number of local variables in a single scope, in a single block, code block. Yeah, things like that you will hit when you are generating a lot of code. Okay, and for the runtime, it all depends on whether you want to add the common code into a runtime library or just generate the code in place when generating code. So it's also a design decision to make. Yeah, some people prefer lean runtime or zero runtime. Some people prefer a big runtime and a minimal code generated for each program. It's also personal preference. Each approach has its own, constant benefits and disadvantages. Yeah. And the next we see, where the place for Lua in the DSL world. So it could be the target language, as we talked about a lot already. But it also depends, as I said, it may not always make sense. Yeah, like sometimes you're generating SQL queries, right? for database. So in that case, make no sense to generate code in Lua. And also Lua can be a good candidate for implementing the compiler itself, because Lua is small and also has a lot of advantages, as I mentioned earlier in this presentation. And yeah, using Lua for the compiler, that doesn't mean that you have to use Lua to write a compiler. I never did that actually, but many of my DSL compilers are actually driven by Lua, because I use another DSL to create DSL compilers, and this Matter DSL compiler generates Lua code. So that's the magic of DSL also. And yeah, sometimes the source language can also be Lua. That's also a very interesting case. I will also show this second example in this presentation. But in that case, oh yeah.
Sorry, Yichun, I just want to just making sure that I understand the idea. When you say used by compilers, you're talking about compiler tools, for example, building, or not the ID, not the. I know, for example, Premake is something that you can use Lua with C++ to build, to help build your projects, right? Is that what you mean by compilers? That you can use Lua, expose Lua to script something for the compiler to run or the build system to run?
So that's commonplace of computers. Yeah, I agree. So basically, it depends on what you are trying to do. So what I've been talking about is DSL compilers mostly.
Oh,
okay. Yeah, DSL compilers, they take a language defined by yourself and then generate another language already understood by the computer.
Yeah, got it. Yeah, the same way, for example, you mean the same way, for example, in the early years of like before C++ or something, people had their own kind of object-oriented programming, changing like the preprocessor of C, right? So you kind of have your own DSL, and then you use that as not Lua, but you use something else to generate the kind of the DSL code for their own object-oriented version of this kind of C that people used to have.
Yeah, right. So that's why the first advanced programming language compiler took so much effort to build, right? Because before that first compiler, there's no advanced programming language. Everyone is writing assembly language code, right?
Absolutely.
Yeah, the first compiler, advanced language compiler, is Fortran, right? And that compiler took so much effort to create, because that was even before the compiler theory was created. There's no theory, there's no algorithm ready to use, and people use a brute force effort to create the first advanced programming language compiler. Yeah, and also another example is the C++. The first C++ compiler, if I remember correctly, also generates code in C code. Yeah. The first generation of C++ compilers. Yeah, so for here, our DSL compilers may generate C++, may generate Fortran. It's higher. It's on a high level, like a food chain, right? The DSL might just sit on the top of the food chain. So basically, we just generate something already understood by the computer. So for the first advanced programming language compiler, for example, the only language the machine understood at that time was assembly language or machine language, right? So it's like a building up the layers and form a food chain or food web.
Almost like transpiling in a way, right? Just transpile to the, you can use that to transpile to the native language, and then the compiler takes from there.
Yeah. Transpilation is also a term, yeah. But transpilation is, I don't quite like that term, because I also like the building up the abstractions, right? The abstraction layers have to be higher and higher. It's not about portability, right? Yeah. Okay. Any other questions? No? Okay, cool. Yeah, so there's also a very intriguing, point here in the compiler world, which is the self-hosting, the concept of self-hosting. So you implement the language in itself. Okay, so that's also very interesting. It has some very interesting consequences also. And for example, many C compilers are written in C, right? So to build such C compiler, you need some older versions of the compiler's binary, right? If you lose the binary of the C compiler in the world, then you lose your code can never run, right? So you have to have some kind of binary code for a self-hosted compiler. Otherwise, the circle cannot be broken. Yeah. And also there's a lot of recursion when you are doing a self-hosting compiler. You have your brain can go crazy when you're writing such kind of things because there's so many loops, so many recursions there. Okay, but it's beautiful. Yeah, many languages or compilers do that, but it's limited by general purpose languages because for the domain-specific languages, they may not even be Turing complete. Not to mention to implement a full-fledged compiler in such a language. Okay, so yeah, it's a beautiful world, I say. Any other questions? Okay, the next one. So yeah, for self-hosting language, I'm talking about language implementing the compiler itself. Okay. So the target, the source language is the same as the language used to implement compiler. Yeah, so some people like to use a triangle. So 3 boxes are arranged in a triangle. Compiler is lower in this diagram. And so 3 languages are involved for every compiler. One is the input language, the other is the output language, with the target language, and also the language used to implement the compiler itself, right? So it's 3 languages are involved here. They could be the same. It could be the same, but usually they cannot be exactly the same. Okay, 3 cannot be the same. Yeah, usually 2 of them can be the same, like the input and the compiler, or the compiler and the target, right? Or it doesn't make sense for the source and target to be the same. But it still happens in the real world. So for example, some compiler may just do code prettification, right? to add a nice indentations, nice spaces to the code. Or sometimes the compiler may just do some validations in the code. Yeah, so there's or do some transformations for portability. Yeah, like the sugar some advanced language features to lower level language features already supported by the existing compilers. Yeah, there are so many such cases and so many different use cases. Okay. So this is not really a DSL. Maybe JavaScript was invented as a DSL to be to be embedded into a web page, right? In early days of the internet. But now definitely JavaScript has grown into a full-fledged general purpose programming language. But we still do this thing as an experiment. We call it ORJS compiler. That we can see the diagram here. So it takes the JavaScript code and then generates Lua code. Transcompiler, right? So yeah, in your definition. And it has many advantages because you can reuse the whole OpenResty or Lua ecosystem, and to enjoy all the benefits of the minimalist, the minimalism of the Lua implementation and Lua JIT implementation. We can see that for some simple example, like a Fibonacci example, a non-recursive one, ORJS 30% faster than V8. And it also takes like 70% less memory than V8 for a non-recursive Fibonacci JavaScript example. So D8 is used here, and even more, 80% less than Node.js. Where Node.js is much big, it's all even bigger than D8. It's very broadened. But you know, JavaScript is very popular nowadays. Virtually everybody knows something about JavaScript. And also the ORJS runtime can include the full OpenResty NX binary. And also we provide the non-blocking IO, coroutines, live thread, everything is now transparent in JavaScript. We don't need to use a very explicit like await, things like that in the JavaScript world. Yeah, that in my opinion, that's stupid. It's simpler, it's more beautiful than the good old days callback hell, but still it's not very elegant. Okay, so this is an example, not a DSL, but a full-fledged compiler. Yeah, so for this thing, we also have the problem of, for example, emulating or implementing advanced JavaScript data structures in Lua, because in Lua you only have tables, right? So in JavaScript you have a much richer set of data structures, like dictionaries, like arrays, like other things. So and also first order object-oriented programming, yeah, things like that. You can emulate things in Lua, and also but still with some extensions to make life easier. Or make the resulting code more efficient. Okay, so here we go. We extend the Lua JIT implementation, and sometimes even the Lua language to make DSLs compilers' lives much easier, and also making the resulting Lua code much more efficient. So the first thing is per-compatible record expressions. It's also possible in standard Lua interpreter, of course. We just make it easier in OpenResty's context. So it's PCRE. We embed that into it. We will see in a minute that why a powerful record expression is important for implementing a DSL compiler or a compiler in general. And also the expression level do and blocks. Okay, I mentioned that function closures are very flexible and very powerful in Lua for generating code. So this is for the target language, by the way. But it has a drawback because you have to create a closure, right? So closure is expensive. It's a garbage collectible object, right? And also your closure has to, you know, reference some, you know, context local variables. Right, so which in turn create more up values, and the up values are also garbage collectible objects, right? so a single code block, you need to create at least several new GC objects, which is very wasteful. You cannot beat V8 this way, right? And yeah, so that's why we introduce a new do and block on the expression level. We change the parser, we change the logic implementation to do that. In this way, you don't introduce up values when you are referencing local variables in outer scope context. And also, yeah.
May I ask a question? Because when you introduce a do and block, then it's more or less equivalent that you are doing a function that is called just once in a fixed place. Have you considered, yes, an alternative solution would be to just implement an optimization that when you write a function, and the function is called exactly where it is declared. You don't need to create up values. You don't need to create the closure. You could create exactly the same code you create for a do and block, but keeping the language simpler without having to add something new to the language. So how do you judge this? How do you compare these two solutions?
Yeah, that's a good point. Okay, so there are actually several alternatives to this. Okay, so So one alternative is, as you mentioned, is the generating to change the control flow, right, and the data flow of the resulting code, and make sure that there's no need for a closure or a function or do end block at all, right? But this thing, such kind of thing it's not easy to implement, because you have to change the control flow, you have to reorganize the data flow to make sure that there's no need to do such nesting, right? You essentially you unwind the data flow and unwind the control flow. That's a lot of work. It's more like the traditional compilers doing SSA analysis, data flow and control flow analysis, and I don't think it's worth it. And because from the performance perspective, for example, the Lua just-in-time compiler can do such SSA analysis already, so it can already do the optimizations. So it's a waste for us to reinvent such deep analysis and complicated analysis, which is context-sensitive analysis, in every single DSL compiler or even non-DSL compiler. So that's a major consideration here, and that's why I mentioned that being composable is essential. It's essential for source-to-source translator, because that makes life much easier. So consider that how you generate code. You have an AST, right? So you can do a bottom-up composing process. So every node generates code by composing the code of its children, right? So it's a recursive bottom-up approach. So essentially, at the root node of the tree, you already have the whole program ready for the resulting target language, right? So that's the easiest one. But if you have to, for example, to reorganize the AST or other forms of the IR, like the SSA, that's a totally different story. The engineering effort will be much more. Okay, so that's one way, and there's also another way, another compromisation way. If we don't touch the Lua implementation, what we can do, we can create helper functions outside the current function. Okay, so the helper function can take a table as an argument, which is used to emulate up values, right? To emulate up values. So we do an explicit key value, mapping in the context table as an argument, and then in the helper function we use a name to reference up value. So you can see slower when for initializing the context table, and also looking up the context table, right? So it's something like that. I can show you the code. You can see my screen, right? Okay, so for example, we create a helper function like a helper one. The ID can be incremented, right, by the compiler or whatever, and then we accept the context argument. Yeah, and in some other code, in some other context, we can initialize the context table here, like the up value 1, 32, up value 2. Hello. Yeah, and inside the helper function, we can reference explicit emulate up value like this, right? Or just plus up value 2. Yeah, we can do something like this, right? And then here we can call the helper function here the local result. Yeah. Yeah, the context function might be, recycled some table pool. Yeah, well, I'll omit that detail here. So we don't have to create this new GC object here, right? And we don't have to create a new GC object for app values, right? Yeah, and this context table can be recycled, like put into table pool here once we no longer need it, right? And to fetch it, we can and get from table pool here. So that's an optimization. Okay, so we can comment out here. Yeah, so essentially the code will look like this. And then we generate helper functions here. Yeah, but still, you still have to create a GC object right here for a static function helper. Yeah, they can accumulate fast. Yeah. Even though you're not creating new GC object on the hot code path like here. So this is a hot code path, right? But still, you have to create new GC object beforehand. And accumulated helper functions can still, adversely affect the runtime performance because the GC still need to scan all the GC objects to do a full GC cycle, right? And if we have a do block, then what we can do, that's much easier. And also the performance is very optimal. And for example, you can just do here do and up value 1 plus up value 2, right? Without all the overhead here. Those things all have overhead, right? All these things. Yeah. So if we use functions, we can we do things like this. The original, the most naive way is to use local result function, right? And we create a closure and we call it right away, right? And here we just use up value, return up value 1 plus up value 2, right? The code is short, right? It's good, but it's very expensive. You have to create 2 GC objects for these 2 app values and another GC object for the closure, the anonymous function. Yeah, so 3 GC objects in this example created on the hot code path. Yeah, but the good thing about this most naive way is that it's composable. Okay, and all 3 ways are composable. Okay, so this is also composable. Even though we need to register a static helper here, but it's easy. We just have another data structure to collect all the static helpers, right? And increment the counter when generating the helper's name, because the static helpers cannot be anonymous. It has to have a name, or at least an implicit name, like in the helpers table, right? So you have an implicit name, like 1, 2, 3, right? So this is an implicit name. Oh, sorry, this is not a colon. Should be equal sign. Sorry, too many languages in play. Okay, and here we can have the anonymous function helper here, right? And yeah, this is slower as compared to a named one because Logit has a chance to actually inline this local function, right? So for this table lookup, helper lookup is slower. Yeah, that's something to consider. Yeah. Okay. Yeah, Python is harder. I won't bother covering Python here because this is not a Python shop. Okay, and yeah, for C. Yeah, C, I think it's worth mentioning C because the standard rule interpreter is written in C, right? So C is not beyond scope. For C, it's tricky for the standard C. Actually, for the standard C, it's a little bit tricky because you have to return a value, right? You cannot just use a code block. You have, but fortunately, if your compiler, your C compiler supports the so-called statement expression feature of GNU-C, then you can do that. We can just write this thing. Yeah, just like an expression level do block here. Oh, sorry, I missed a return here. Okay. So basically, you can put arbitrary sequence of statements on the expression level without introducing new closures, new functions. Okay, so that makes the code composable. Because each component of expression can be code blocks themselves, right? So that's why it's composable. And GNU-C statement expression, yeah, we can see statement expression. We will see. Yeah, that's a official man page here. Yeah. So basically, yeah, there's no return. So the last value, the last statement's value is return. Okay, for this expression level statement blocks. Yeah, it's very handy. Thanks to the statement expression, C can also now be compilable, and a C compiler, optimizing compiler, can do a very good job in optimizing everything. Yeah, so that we don't have to do that. So reusing work is important because we may need to create a DSL compiler just in 1 or 2 days, right? So we don't want to spend too much time on all those bloody details. Okay, cool. So let's go back to the here. Go back to the list we do. Yeah, the do and block. We will show an example, more examples later. And also go-to is important. It's so important that it's a must-have for compilers, especially when you are implementing more capable languages, like JavaScript, right? So with go-to, you have the ultimate freedom to do arbitrary control flow generation. Okay, so yeah, for example, Lua doesn't have a continue, right? With go-to, it's very easy, trivial to emulate. You don't have to restructure the control flow of your original language and just let the Luajit compiler do the rest. Okay, so go-to is not added by ourselves, it's added by Michael. I think other people have similar use cases like us. Okay, and also there's some table, new APIs. They're primitives, so they are not implemented by some slow Lua extensions, not even C extensions. It's part of the VM, so that it can be very efficient and can be in line directly by the JIT compiler of Luajit, like table new. So you have a chance to pre-allocate memory finally when creating a new Lua table. It helps a lot, actually. In our experience, a lot of industrial customers, industrial users, for their online Lua applications, a lot of time, a lot of CPU time, valuable, precious CPU time is spent on growing Lua tables, unfortunately, and it's handy, right? For order growable Lua tables, it's always handy to add more keys, add more values into the tables, but it also comes with a cost. For hash tables, you have to rehash. For arrays, you have to extend the storage, linear, contiguous storage, and then copy data over, right? So those costs can accumulate very fast. Yeah, so with the pre-allocation option, plus the table recycling mechanism like a table pool, it can work very well. Okay, and also we have a fast table clone primitive implemented in Luajit. It's a shadow copy, not a deep copy, because deep copy is too tricky. And the shadow copy is already sufficient for 99% of the real world use cases. Yeah, and also N keys. It's much faster than, for example, the sharp operator, and also sharp operator has some pitfalls, right? Everybody knows that, and they also cannot count hash table entries. They only find them one of the local max index, right, for a table. It's not even a global max. N keys is a different story. It really count all the keys, no matter if it's an array entry or it's a hash table entry or included. Okay, and it's array table dot is array is also another Luajit primitive Lua API. So it can efficiently test if a table is an array under the hood. Okay, I know Lua language try to hide everything, right, behind the table, try to make the table looks like a generic dictionary, be it array or hash table or whatever implementation it might be. But for ultimate performance control and also for efficiently emulate other, more fine-grained data structures in high-level languages, other languages like JavaScript, we need to distinguish array and hash tables, especially when you are trying to generate in JSON, right? JSON doesn't have a concept of generic table. You have to distinguish arrays and hash tables. Okay, and also it's empty. It's a quick way, much faster way than using the sharp operator. And also sharp operator won't work on the generic object hash tables. Okay, so there are many such things to make lives easier and also make the DSL compilers Lua output more efficient. Okay, and expressions, yeah, expression. Lua's own expression is slow. Okay, so it's the interpreter per se. It's not it doesn't even come with a JIT compiler, not even in Lua JIT, and also it's limited. It's useful for 90% of the use cases, but for the remaining 10%, it's very limiting. So that's why Perl-style regular expression is so helpful, especially when you are using Lua to implement a compiler, a very complicated parser for a complicated language, like C language, right? Like JavaScript language. It's very complicated, much more complicated than Lua. Okay, but still Lua is not easy to parse, frankly. Many people may think that Lua is a simple language, but it's a simple language to learn, not a simple language to implement. The grammar, the Lua's grammar, it's a secret. So the Lua grammar also has some, hidden pitfalls. I didn't realize that until I actually tried to implement a Lua parser. That's a completely different story. Okay. Yeah. So let's focus on the expressions, regular expressions. So several very nice things about Perl regular expressions is that why is the look around support, look around assertions. So basically it won't consume any input. It's like assertions, like a carpet sign for matching the beginning of the line or the beginning of this input string. Also like a $sign. Those things are zero width assertions. They don't consume any input. There are also more advanced versions of that, which is look around assertions. So for look ahead, you don't consume the subsequent input, but just look ahead, right? By definition. And to check if the subsequent characters match something. If not, then the whole regular expression failed to match. Okay, so it's an extra, assertion. And look behind is similar. You match behind the current matching position, and to make sure that the already matched stuff or already skipped stuff match certain things. Okay, so the match ahead and match behind. It's very helpful when you are writing a parser, a lexer. Okay, so for example, to the first example here. Oops, I cannot select here. So here we try to match an identifier. It's the most common thing when writing a parser, right? But you want to skip keywords, okay? Because keywords or reserved words cannot be used as an identifier by definition, right? So one easy way is to use a look ahead assertion here, to skip all the keywords in a list connected by the alternating operator, right? And also make sure to add another zero width assertion, the \b, which only matches a word boundary. Okay. Yeah. So anything here can be a true identifier, excluding any reserved words. Okay. So so here is another thing to disambiguate. Disambiguate is very important in a parser. I mentioned the context-sensitive parsing, right? So you need sometimes you need a context, some kind of context to disambiguate, to allow very flexible grammar. So here we match two vertical bar characters, but they cannot be followed by an equal sign. Okay, this is a look ahead. negated look ahead because that's another operator. The vertical bar and the equal sign, that's another one. Okay, and here a third example. We want to, for example, our DSL allows omitting semicolon if and only if the following one is it's a curly braces, closing curly braces. Okay, so here we just write a look ahead, but we don't consume that. Okay, so the semicolon or closing curly brace. Okay, so the also this one is also doesn't consume any output here in the assertion. It only consumes the leading spaces or new lines. The \s matches any white space characters, including new lines, tabs, spaces, vertical spaces, things like that. Okay. So yeah, so writing parsers, we need powerful regular expressions for powerful lexers. And recursion is also a very nice new addition to the Perl style regular expressions. So here we match a Lua comment. Can you see that? Can you recognize that? So including a line comment. Okay, so here this part is a line comment. You can see my this way I can select. So this one is a line comment. Okay, and both line comment and this is the block comment. Okay, in Lua. Okay, and both of those comments are led by double dashes, right? Okay, so line comments is easy, right? So you match anything, not a new line character until reaching a new line or the end of file, right? And the tricky part is the long bracket, right? The long bracket notation in Lua is tricky. That's why I said Lua is not an easy language to implement, to pass. Sorry, I mean to pass. And here we match any equal sign, any number of equal signs here, and we also match exactly the same. It's important. It's the same length of the equal signs for the clothing part, right? So here we use the \2 is whatever matched by here, by this subpattern, right? And we ignore whatever in the middle. Okay. And for C comment, it's actually easier, right? For C comment, we can just write, we can just use this dot, the non-greedy version of the dot, star and question mark, right? So for how to match a C comment. Slash, right? And we need to escape the star sign. Star sign asterisk is a meta character in Perl regular expression. And then we, oops.
Sorry to interrupt you. I just want to give you a quick time check. We have about 20 minutes left, just so you can kind of plan the ending and any additional Q&A.
Okay.
Thanks.
How many times I have used? So it's a 10:21 already. Okay, so half an hour already. Huh? For 2 hours. Sorry, it's already.
Yes, usually the class is about 90 minutes, so we've used about 70 minutes of it, or 80 minutes, but we can definitely go a little over today. So
okay.
I think about 20 minutes more is totally fine.
Okay, cool. Thanks for the reminder. Yeah, I forgot the time. How time fly. Yeah, so for C or C++ comments, we can just use things like this. Yeah, if the spaces are insensitive in the regular expression, yeah, we can keep them. Yeah, but here if they're not, then we can write things like that. Yeah, so this is the way we measure C block comment, right? Or C++ one is also very easy. It's just line comments, right? The C+ line comment syntax. Yeah, we can just use something like this. Yeah, comments are common, right? For any languages. Okay, cool. it goes much slower than I expected. Fortunately, I didn't prepare too many slides today. Okay, cool. So recognitions. I just mentioned a few. There may be other features, but these two are the most important ones, which are missing, at least in the the standard Lua interpreters patterns, like string match patterns. But they might be able to emulate that with LPEG. Okay, LPEG is more powerful. It's a combinator parsing library, like Haskell's parse. I have experience with Haskell's parse, but I have very little experience with LPEG, frankly speaking. And okay, cool. Yeah, for composable Lua code, yeah, I already mentioned that. So we can, like a Lego, right? Lego toy. You can compose different things to build bigger and bigger stuff, right? Like a castle or like a ship. You build things with little pieces on different levels, and then essentially assemble everything together to form the final big thing, right? So here, the good old way is using closures. It works, but it's very slow, painfully slow, actually. And the new way using do and blocks. Yeah, but in the Middle Age, we use the helper way, the static helper way. The performance is much better actually after we migrated from the helper way to the do and block expression level, do and block way. Sometimes it's almost 80% speed up for a full-fledged DSL compiler. Yeah, that's quite a thing. Okay, and yeah, because it happens everywhere, so it's so frequently executed. Because so little bits matter. They accumulate very quickly. Okay, so here's the thing: our compilers run by Luajit, but we don't write Lua. Okay, so we invent a new language specifically for creating compilers, not just DSL compilers, but virtually any kind of compilers. So this language is inspired by Perl 6. It's called Raku nowadays. So I'm a Perl fanboy, as you can tell, like the Perl expression part, right? But I'm also a Lua fanboy. I just don't want to write too much Lua code by hand. I like to use it as a IR, intermediate language, okay, intermediate representation for complex things at least. Okay, and Fanlang, we call it Fanlang, it's a dialect of Perl 6. Ironically, our implementation was done just in a few weeks, and it's already times faster than the official Perl 6 compiler, even both for the compiling speed and also for the resulting code speed. It's a complete win. Okay, and the Fanlang compiler itself can be self-hosted. Yeah, I mentioned self-hosting right earlier. So it could be self-hosted, but it hasn't. It hasn't. It's still written in Perl 5. Okay, and we didn't have a chance to rewrite it with Fanlang itself, but we could. Okay, because Fanlang is completely capable of rewriting itself, compiler. And why Perl 6, you may ask? So I try to be fair. Over the years, over the decades, actually, I'm actually older than I appear. So over the decades, I actually tried many different languages, many different libraries, toolchains to build compilers, including the C, C++, Java, Haskell, Scheme, Python, and Perl. Many language. By Perl I mean Perl 5. Okay, many library, many different ways. But I didn't find my true love. Okay, until I see Perl 6. But even Perl 6 isn't perfect. That's why I change it. That's the beauty of implementing the language yourself. You can always change it. Remove things you don't like, add things you like most, right? So So the Perl-6 is designed because Perl language is designed, was originally invented as a text processing language. So its text processing power is unique. Really. And the Perl-6 pushed that to the next level. So the Perl-6 regular expression is actually a full-fledged recursive capable, grammar engine that can do the parsing. But still, I don't like it. So I totally rewrite it, redesign it to form our Fanlan grammar engine. And you can generate, of course, it generates Lua code, okay, and it runs optimized for logit, runs very fast, and also it's very lean and minimal. Okay, and almost all our compilers are written by Fanlan. At least those non-trivial ones, most of them are non-trivial anyway. And we for Fanlan compiler itself is written in Perl 5. You take a Fanlan code and then generate Lua code. So most of our compilers are written in Lua, of course, just not by handcrafted Lua, but machine generated Lua. Okay, so here's a very minimal example just to demonstrate the idea. Okay, so this arithmetic calculator. It's an infix, natural mathematical notation calculator later. And we define expression and, oops, let me oops, play from start, that's wrong. Should be. Yeah, so the expression, so here, okay, I cannot select anyway, so it's a picture. Okay, so expression is the term rate. So each term, it can be multiple terms connected by add up. So this rule, add up could be a minus sign, could be an addition operator, right? And it could have leading or trailing white space characters. And each term is defined by factors. Yeah, I think you may recognize that from the LPEC rules. Yeah, they're similar, but I think it's more powerful. Okay, and the factors connected by multiplicative, hard to pronounce, multiplicative operators. And the multiplicative operators can be division, could be multiplication, and factor could be connected by the power operator, right? And an atom could be a number or parenthesized sub-expression, right? A number could be integer or a floating point number. You could add more, exponential notation, scientific exponential notation here. Yeah. So this is a parser grammar, okay, and you define a class. Oh, sorry, this part can be omitted. It's not related. Yeah, and you can add another class to do the EST manipulation. So for example, if you match the term, then you do multiplication or division according to the operators. So this example is incomplete. There should be another class to build the AST or just do the calculation in place. Okay, but it's very simple and also very scalable for even a full C language or Lua language. Okay, yeah. So here is the context sensitive analysis part. So we have a look down helper that you can match a certain EST node. So here the key is an array, the argument is an array, look down's argument is an array. So each key is a EST type. Okay, so for each EST type, we can have a handler, a closure, right? A function to do a process like replacing the node, doing in-place EST nodes, transformations, or just to collect information from the EST. Right, so that's the so construction EST part. Yeah, I don't have an example here. But so basically, you define a class with a method, and each method just build the AST from in a bottom-up approach, right? Just like the code generation using a bottom-up approach. You build the leaves first, and then the second layer until you get everything on the top, which is the root node. Okay, so it's a very standard algorithm or a paradigm. Okay.
Does the Y in Y-lang stand for Yichun?
Yes. Another reason that Y stands for answering questions about why about running software systems.
Exactly.
Yeah. So HLAN is it's a gateway, you know, DSL. I just show you some DSLs. Okay. So we designed that for high performance distributed web gateways, traffic gateways, for our customers, and basically so it's a rule-based language. Okay, so even when designing a DSL, you don't have to design some exotic syntax from scratch. You can still, you know, get inspiration, get some ideas from existing languages or from existing disciplines, right? So rule-based languages is a perfect fit for this domain. Yeah, you just find the most natural, you know, notation for the current problems. Yeah, so we can click on here. There's a public user manual here. If you're interested, you can look it up. Yeah, it's a full-fledged programming language, not a programming language. It's a gateway language, okay, but it still has a lot of, you know, common sense. Yeah, like the operators, string operator, bit operators, arithmetic operator, relational range, ternary operators. Yeah, and also identify variables, custom defined variables, scoped variables, right? And the function name, functions, custom functions. Yeah, many different booleans. Rules could be multiple conditions, right? And or all together, yeah. Multiple actions, yeah, and code blocks even, yeah. Action blocks as expressions. Yeah, I don't have the time today to go through everything here. If you're interested, you can look it up. Yeah, for HLAN, it generates Lua code, and the compiler is written in FanLang, which is also in Lua per se. And let's go back to the slides here. Yeah, OpsLang. OpsLang is also very interesting. So basically, you can automate the command line console of a Unix, like a Xterm console, right? Using it's kind of similar like the expect languages, the expect package of the TCL language, but it's much more powerful. And it's in Lua. The resulting code is in Lua in OpenResty, and we're doing non-blocking streaming matching of the console. So it's for DevOps automations. And so here example, for example, we run the RPM build command array, and then we're using a stream block to match the output stream with standard error and standard out. So when the output says enter passphrase, right, and we set a key because it's empty password, and then we redo the stream until we find another enter passphrase. It's like a loop, right? But it's more natural. And until we find a prompt, right, and then we break out. We also have a built-in timeout. So when timeout reaches, you also break out of the stream looping. Okay, it's a very simple example. More complex examples can be found here because it's so powerful. It generated Lua code. The compiler generated Lua code, and using OpenResty's non-blocking pipe API for the actual, you know, implementation. Yeah, it's a very powerful language. And also generic, not just for shell. You can, for example, automate the telnet, the GDB interactions, right? The prompts, any prompts. You can define your own prompt. It's very generic. Anything on a console can be automated. It's a low-level thing. Yeah, and it's variables, define variables. Yeah, array variables. hash variables, capture variables, regular expression is also first citizen in the DSL. Yeah, it's very handy. So regular expression is everywhere. Yeah, we can also even embed Lua code into the ops language, the DSL. Yeah, because DSL can be limited, right? So if you need something quick and dirty, you can embed another language, generic code language into the DSL, right? Like a Lua code block. Yeah, so yeah, it's not hard to parse actually. You just need to be careful about the Lua long brackets, right? Skip long brackets and the string literals, right? Yeah, and also pair the. Oh, you don't need to pair anything because the outer layer is curly braces. Yeah, you need to pair curly braces so that you can find the end of the embedded Lua code block. Yeah, Lua a little bit tricky, but still it's not too hard to embed into other languages.
If you try to keep it simple, it's okay, I guess. If you just pay attention to these things, yeah.
Right. Yeah, so you don't need a full Lua parser to skip the Lua code block, right?
Yeah.
You just need to find the terminator when the Lua code block ends. Yeah, that's all you need. Okay, cool. So let's go back to the opsland. Yeah, we can actually take a look at the opsland compiler itself. So here, yeah, how many lines do we have? Yeah, we can see the. Oops. Let's keep the. Yeah, so the fanlang code is in .fan file extension naturally, right? And the parser, the parser is in the grammar module, right? So we have the rules defined here, yeah, and we'll have another AST module defined so that we define the method of the same name in the grammar rules. And then the method will call automatically when a certain rule is matched. And then we build the AST node using the new constructor, a class new constructor to build the AST node, and we assemble them from bottom up. And on the top is the top rule, and the top AST node is the document, opsland doc class, right? The AST node class. And then the children is passed in via the parameters, all the statements, right? The statements, and then passing to the root AST node to form the whole tree. Okay, so it's a bottom-up approach. Okay, and the code generator, yeah, the code generator actually in our design is actually distributed in each AST node class. So for example, we have like a variable AST node right here, opsland var. So this is the class name, and the parent class is a value expression, and then we have the method like oh, okay, it doesn't have a Lua generator because it inherits from the from the parent. Okay, so I take another example. Doc, we have a oops, no Lua. Use. Okay, so this has a Lua method. So code generator is in a different AST class, so it can also be called recursively. So the doc calls all the children's as Lua method, right? And each node in turn calls their children's as Lua, and they assemble the final Lua code in a composable fashion, right? From the leaves to the top to the root. Yeah.
Sorry to interrupt again. I know Roberto has to leave in a few minutes. I want to try to open it up for one or two more questions if we have any, and before we wrap up class today. Are there any outstanding questions from anyone? Feel free to type it too if you'd like. Cool. And also, if you want to wrap up anything for the last
Oh,
2 or 3
yeah.
minutes here,
Okay, cool.
I want to give you a chance to do that as
I
well.
still have a few slides, so yeah, I'll go through them very quickly. So schema-land, you define a data schema and then generate Lua API and SQL queries for databases and SQL definitions and the RESTful APIs with data validators, right? Everything. So basically, you just have a single centralized schema specification with all the constraints, all the types, all the field data structure defined. Yeah, so it's a very handy tool for creating Lua web applications, for example, database-backed web applications. Yeah, and we also have dynamic tracing languages, which do not generate Lua code. So the source language, the input language could be Lua, like Lua. If you are interested, you can look up the link. The public documents are available to everyone. And Ylang is a full-fledged C compiler. Okay, so they can take the C input language and generate like syntax scripts and the eBPF C programs, yeah, for dynamic tracing to analyze software performance, security vulnerabilities, and the functional bugs, yeah, all those kind of things using a non-invasive way. So zero changes are made in the target processes. Okay, so and YSQL is a SQL variant that you can treat any running processes as a relational database, and they can query against it to collect deep deep metrics directly from those processes without their collaborations. Okay. Any other questions? Finally, all the slides are over.
I just have a very quick one. So whenever you are building something like this, right, you have all these tools, all these languages. How was the evolution of them? Because of course you don't build these things and they don't get to the stage that they are in 2 days, right? So
oh yeah, of course.
How is the, like, do you get user feedback to decide what things to add? Do you, how is the kind of this ping-ponging ideas between the community, and how do you decide what to add and how to evolve this type of DSL?
Oh yeah, that's a good question. So the major inspirations from my own observations with the real world business software systems like in Alibaba, in Taobao, in Cloudflare, right? So another source of feedback is from the community, because I also manage or maintaining an open source community, OpenResty. So I see what people are talking about, what people are complaining about, and what problems they are having every day. So those things go to a mix and generate the final solutions. In my humble opinion, what should be the best, or what should be the
you are the benevolent dictator that decides what goes into the language. After all, I think you make the final decision.
Oh yeah, of course. Yeah, I
okay.
make the final call. Yeah.
Good.
Hey, Yichun, it's Genders here. I don't have a question. I just want to say hi, and also I'm just really impressed with seeing how this has grown. I remember it from many years ago at Cloudflare, and how things have evolved after, and it's really impressive. Done a lot of great work.
Oh, thank you. Any other questions?
Great. Well, I think we can call it there. Thank you for such an incredibly insightful talk. It was really impactful hearing from someone who's had such an impact with Lua and on so many industries, as we were just talking about. So thank you so much. I want to give a quick update to the class, a reminder that next class, August 27th, is the last live class, same time, 9 a.m. Pacific time. And the final project is going to be due on September 10th, and we'll be discussing more on that in the next class as well. So thank you all again for a great class this week, and we'll see you next week. Thank you again.
Thank you, everyone.
Thank you. Thanks everyone. Bye-bye.
Thanks for the talk.